Okay, welcome to episode 1 of the Signal and the Noise Guide to Large Language Models. In this episode, we'll be discussing from text to tokens, how the machine sees you. This episode is an introductory episode to the basic fundamental processes that go into large language models behind the scenes. If you're already an expert, you probably want to move on to the next episode. This is really for people who don't have a background in it, to sort of get up to speed with what's actually going on. So we'll look at what actually happens when you create a prompt, understand how the model goes from a list of numbers to something that looks a little bit like thinking, and we'll discover where model consensus comes from, what the implications are for your prompting and for your large language model use. So part 1, the illusion and the data. When you type something to a chatbot, you may think you're sending words, but you're actually sending it numbers. So you might type in something like, who is the fastest runner? But the model actually sees a string of numbers. They don't know what verbs are, what running is. They just know that the letters runner occur enough times in the training data for it to be relevant. This is called a token. Tokens are the building blocks of large language models. Token is a word or a subword that's frequently seen in the training data. A rule of thumb, roughly 750 words is about 1,000 tokens. Here's a couple of examples of tokens and words and subwords, how they're split up or how they may be split up. So a common word, something like apple, which will be seen quite frequently in the training data, would be resolved down to 1 token. More sort of compound or complicated words will be resolved into more tokens. So, for example, isn't would probably look at the is and the nt, making that into 2 tokens, and then sort of more like longer words. For example, here, undefinable, undefined, and able will all occur more frequently in the data than the word undefinable by itself. So it gets split up into in this case 3 tokens. They're generally generated using a greed algorithm from the training data. So this looks through the entire training corpus, all of the words, all of the language it's been trained on, and determines which chunks of letters appear the most frequently. So, for example, THE is going to appear quite a lot. And again, our previous example, apple. These tokens are then represented as integer numbers, or whole numbers, called embeddings. Large language models don't work on the words, they work on the numbers, they work on the embeddings. So here's a rough conceptual flow of what happens when you send data to a large language model. You send your text input, which is then converted into tokens, which is then converted into embeddings. The large language model then operates on the embeddings and returns a set of embeddings, which are then changed into tokens, and then these are converted back into output text, which is what you see. So you see the white box to the white box, but the grey boxes in between are where the real large language model work happens. So to reinforce this, they don't actually understand what the words mean, just that the letters are often together and that the numbers then have a relationship to each other. This can be a problem if your training data is straight from Reddit or other sort of low quality sources. For example, usernames can appear unreasonably frequently, particularly for power users. This phenomenon is called glitch token. So, tokens and arithmetic. In the same way large language models don't see words, when you type numbers in, they don't see the numbers as numbers. They then convert them to tokens and then to embeddings, but the embeddings don't necessarily reflect the numbers. Also, a single number might be represented by multiple tokens because of the greed algorithm token breakdown. So this means that doing arithmetic using a large language model just by itself creates an awful lot of problems. So tokenizing algorithm only understands the character group reference, not the relationship between the numbers. So if you have a large number, in this example 34,509, this might break it down into 34, 50, and 9, which will have their own embeddings. But if you change one number, you may completely change the embeddings that are used for the model. So adding 10 to it has completely changed the tokenization and the resultant embeddings. So yeah, just you see I've added the 10, 34,519 now goes from 3 tokens to 2 tokens, and they're completely different. I've used some subscript notation to represent the embeddings since I'm not using a consistent embedding index set. This is demonstrative rather than something you would find in the back end of a model necessarily. So this means that the inconsistent tokenization means that the models do not see the numbers in the same way we do. It doesn't think of it in terms of your ones, tens, hundreds, etc., your base 10 number sets. And the numbers are then written in a special code which changes every time you change the numbers. There are some examples where this isn't necessarily the case. For example, 2 plus 2 equals 4 may be memorized, because in the training data, you're likely to see this quite a lot. But more obscure numbers aren't memorized. You can't remember every possible sum of 2 numbers or 3 numbers. You have to solve the problem slightly differently. It's also worth mentioning here that computers and humans both solve maths from right to left. So if you think back to original sort of mathematics at school, 15 plus 19, you start at the right, you add the units, you add your 5 plus 9, and then you create 4 units, and then you carry the 10. So then you have 10 plus 10 plus 10 equals 30, plus your original 4 gives you 34. This is reasonably straightforward. Most people understand how to do this kind of maths, but large language models see this completely differently. Large language models work from left to right or from start to finish. So the 3 needs to be written before the 4 can be, which means it has no understanding of the arithmetic process that's gone on before it. And all this makes maths very, very difficult for large language models just in their native unaltered form. So how do you go about that? There are 3 solutions modern large language models use. These are tool use, chain of thought, and scratchpad thinking, and improved tokenization. We're going to look at tool use and chain of thought in later sections, but it's worth knowing that they do exist. Improved tokenization can go some way to solving this problem, although it's not a robust and long-term solution. So a quick note on tools. We will discuss them thoroughly later in the program. However, the basic idea is that a maths problem is detected. A maths problem tool is delegated. It will write maybe some Python code that will then be executed, and then the result of the code will be reported. And this will be included within the output of the large language model, rather than solving it on a next token prediction basis like it would do for words. You can also use chain of thought or reasoning models, which take intermediate steps. So, for example, 1, 2, 3 plus 4, 5, 6, your model might understand that it should break down, or not necessarily the model, but the system that the model is attached to will understand that it should add the units, then add the tens, and then add the hundreds and get an output. But tool use is by far the most robust way of doing this. Some models like Llama 3 use a pre-tokenization, but it is less effective than tools or chain of thought. Okay, so part 2, from numbers to narrative. This is where we start to get a little bit more into the understanding of what the large language model is doing, how it's working. So like we mentioned before, they don't think in a human sense. They understand geometric relationships and probabilities between different tokens. So reasoning just becomes very sophisticated pattern matching across huge probability spaces. We must shatter the illusion that a large language model is looking at a dictionary. It's looking at a map. It's not looking up and referencing things in the same way that we would. We don't go away and read a paper, read an article, read a website. It just arranges the tokens on the map based on their proximity to each other in the training data. Token apple relates to the token tree, pi, and mac to varying degrees. I've tried to illustrate this on the right, where the closeness or the length of the arrow from apple to pi, mac, and tree is shorter or longer. The more frequently they appear together in the training, the closer they will be on the model map. Here's a larger visualization of semantic clustering. So in your token embeddings go into your vector space, and then you have various semantic clusters. So cat, furry, and animal might be close together because they're all generally related, whereas car and vehicle will also be closer together, but they'll be further away from cat, animal, and furry, and they can be clustered as well. So the next important thing after tokens that we have to understand if we want to understand large language models is the concept of attention. It's probably the most important part of generative pre-trained transformers, or GPTs. What this means in practice is that in your prompt, every token looks at every other token and determines how much weight or attention to give it. It's a massive correlation matrix calculated in parallel. This is why GPUs are so important in doing this. We're taking every word, looking at every other word and its relation to itself at the same time, often for hundreds, thousands, maybe even millions of tokens. So sort of a more practical example of how attention works, what it is, and kind of, we won't be able to solve anything directly here, but we can perhaps get a sense or a feel for what's going on. So I like to use the what is it example for attention. So there are two phrases here. The animal didn't cross the road because it was too tired, and the animal didn't cross the street because it was too wide. As humans who've experience with language, we understand that it, in this context, changes depending on the sentence. So in the sentence on the left, animals get tired, so we know it is most likely the animal. And in the sentence on the right, we know that street is associated with wide, so the it is most likely to be the street. The model doesn't know what a street or an animal is, or what tired means. It just knows how frequently that these words occur next to each other or close to each other in the training data. And because of that, it can solve this attention and understand, or appear to understand, the difference between these two sentences, even though it's not directly obvious. It's not explicitly stated. So another example, this is multi-head attention. So large language models don't just do attention once, they do it multiple times. The model can learn to notice grammatical structures like noun phrases. So for example, the crane in the sentence, a huge crane lifted the heavy crate. It also learns to associate descriptive words with the things that they describe. So for example, the huge crane. Huge is understood to be descriptive, and it can resolve context. So the crane lifted will dissociate from the crane as a bird, strengthening the relevant associations within the attention matrix and from the training data. This sort of what appears to be understanding comes from many heads working across many layers with the specific details across different models. Okay, moving on to part 3, fear of the outlier. So we all have experience reading large language model outputs that feel a bit bland. Often we say maybe it stinks of AI, or it's obviously AI. We just get a sense, we feel that we're reading something that's generated by a large language model. It's important to understand that this isn't a bug, it's a feature. We understand now from our understanding of attention and tokens that common token patterns appear clustered together, and rare, unusual, or extreme ideas are further apart within the training data. During the training, the model learns that predicting common patterns lowers its error, and over time its predictions are drawn towards high density, commonly observed patterns of words. This gives the model better results in its training, but we get a sort of a bland, predictable, recognizable output at the end. It's statistically correct, not necessarily politically correct. The average human is boring. Most of the content in the training model that was created by average humans is also likely to be boring. The model simulates the average human very well. We also have to remember from the model's point of view that the center is safe. It's trained to minimize error, so wrong predictions are penalized. Rare patterns are hard to predict reliably, so high probability token patterns are more common than rare ones. The model learns that being conventional gives it a better score, and giving it a better score makes its training safer. So bland, boring, predictable responses are a consequence of the statistics. They fall directly out of the way the model works. The LLMs try to predict the next word, and to do this it uses something called a softmax function. I'm not going to dwell too much onto softmax functions or the mathematics behind them here. It's beyond the scope of the topic. But it's important to understand that this is how the model turns scores into choices. The model assigns a score to each potential next word that could follow in the string. and the softmax converts the score to a probability. High scoring words are regularly chosen, and lower scoring words that may be interesting or alternatives are lost in the statistics. For example, if red scores a little higher than crimson, it will win most of the time, even if both words are completely reasonable. Another example might be you look out at the sky on a nice sunny day and you see it's blue. It's also azure. Azure will appear next to sky in the training data significantly less frequently. So that'll mean that the boring blue answer will be the one that is selected as the next word most frequently. So we can think of this like a blurry JPEG, a blurry image. So as we compress images, we remove the fine detail. So compressing the corpus of language removes the subtlety and nuance from the language. So we lose things like rare phrasing, idiosyncratic voices, extreme and unconventional styles, and the language feels smoothed out, generic, corporate, or flat. Again, this isn't a bug so much as it's a feature. It's a consequence of the way the models are trained. And there is a real world problem associated with this, and that's now model collapse. So models are often trained on output model data, risking a feedback loop. So the model creates a bland output, which is then agreed and accepted and used by the end user, which then becomes training data, which goes into the next model iteration, and then the cycle continues. More bland outputs, more bland training data, more bland model iteration. It's not inevitable, but the risk is real without intervention. So what can we do about this? This is another language model concept called temperature. The model temperature affects the next word choice. So if you have a low temperature, a highly deterministic, you end up with the same word most frequently. So for example, the cat sat on the blank. What's the next word in this sequence? Mat, rug, floor, and couch are 10, 8, 5, and 2. Mat is the most frequent, but rug is quite close behind it. If you have a low temperature and you apply the softmax function to 10, 8, 5, and 2, you're likely to get mat maybe 90% of the time. But if you adjust the temperature to a little bit higher, your raw scores will stay the same, but your probability from your softmax function will change. So for example, in here we see mat and rug closer to their actual distribution within the raw logic scores. We can control this, we can define this, and we can use this as a tool. For example, if you want something that's highly deterministic, perhaps if you're writing software programming code or something like that, you expect a low temperature, you want a really deterministic output. You don't want the model to go crazy with its token prediction. You want something that will actually work when you compile or run the code. Whereas if you're doing something a little bit more creative, you can use a higher temperature, you can deal with a slightly more creative output, a slightly more variable or less predictable or less repeatable output. The inevitable slide. A language model does not have opinions, it has probability landscapes. It's always safer near the center than at the edges. So the result, as we've discussed, is bland, boring, and predictable responses, Wikipedia style, that mimic the consensus opinion. Sharp edges and weird syntax are penalized in the training, and they won't be resolved when you use the model in the real world. But we can go around this a little bit. We can use temperature, but we can also use prompt engineering to force the model away from where it wants to be and into more interesting territory. Prompt engineering and how to generate prompts, how to create interesting prompts will form part of the next presentation and the rest of the series. So if this has been useful, please like, subscribe, and share, and we'll move on to the next section.